Hi all, welcome you to the new session of embedded software testing. This is the Unit 3 static analysis and code reviews. So there are few sessions in this unit. We study about static analysis uh, and code reviews, inspections, and metrics. So these three things we'll study in this Unit 3. So there are few sessions available in this unit, and we know that testing can be done with the help of dynamic testing. The other context is static testing. So in dynamic testing, we know that we can test when the program is executing. So let's do a recap of what we had studied in Unit 2. Unit 1 will not recap because Unit 1 we already gone through while doing the Unit 2. So Unit 1 was about introduction, basic templates, testing aspects, etc. In Unit 2, so we have studied about dynamic testing, PM method, static versus dynamic testing, its differences. Then as part of the dynamic testing, we studied about black box testing, white box testing, differences, advantages and disadvantages. Also we had gone through the coverage aspects. Then we discussed about the black box testing techniques, and the testing techniques are equivalence partitioning, boundary value analysis, then state transition or event transition testing and fault categories. Then we also had an example and go through state event table. Then model based design and testing, it's called MBT, model based testing. Then white box testing techniques we went through. So we have gone through different techniques under white box testing. They are statement coverage, branch or decision coverage, then data flow testing, branch condition testing, branch condition combination testing, which is nothing but MCDC, but MCDC separately we studied from the D1 and perspective. Then we have modified condition testing, the linear LCSJ testing, code sequence jump, then gray box testing, which is a mix of both white box as well as black box. Then we understood about test driver and test stubs, which are very important in terms of integration or unit testing. Then we go through some of the coverage tools and discussed about different tools that are used for the dynamic testing and analyzers, performance, logic, memory, etc. Then testing tools life cycle, how it is based on a life cycle chart from the standard book what we refer. Then test automation and techniques like automation, batch processing and all that we have studied there. Then the last one is disk based testing and importance of disk based testing and different strategies, how it could be done. So those are some of the sessions in Unit 2 in brief. Okay, so in the next unit, that is static analysis and code coverage, we will try to understand what is static testing. Okay, static testing, a process of evaluating a system or component based on its behavior without executing the program. So we know that dynamic testing has to be done when the program is executing. We do a lot of black box and white box testing techniques followed in the dynamic testing, whereas static testing is a process of evaluating a system or the units of the components depending on its behavior, and the behavior will be checked or verified or analyzed or evaluated without the need of execution of the program, because already we have executed the program and tested using the black box for one aspect of the testing. These are different aspects. This is also equally important to do the static testing. Here we don't execute the program, but the different things are there without executing the different aspects of the inputs from the test artifacts that will be used for static testing. So let us study about that in the next slides. Context, into context with dynamic testing, a process of evaluating a system or component based on its behavior during execution. That means, in contrast to dynamic testing, during execution we will do the test. That is what the basic difference of dynamic testing and the static testing. Okay. The next one is static versus dynamic testing. So basically, to do a testing as an embedded system completely, both have to be done. Some of the things may not be possible with dynamic testing. Some of the things possible with the help of static testing. Some of the things may not be possible with dynamic testing. Some features are definitely not possible with static testing. So likewise, we have a complement of each other so that the testing is complete in all aspects. So that is how these two techniques are mutually done, and while doing that we may take credit of each other so that the coverage aspects are taken care. So static analysis were explicitly used in olden days embedded software testing, where tools availability and affordability were on stake. See, just imagine that there are no tools to test when the program is executing. How we can test it? So it's very difficult. So what used to be done over the earlier days is they used to run, stop, verify on the field, and when the program is halted, they will extract some of the outputs of the memory statically. So there was a lack of tools, embedded tools in terms of testing, and the debuggers and analyzers. These were very less in earlier days. That is why you used to have sort of a code review, more of a code review analysis. It could be inspection. We will study about this how they are done, but in a nutshell, these are the major contributors for overall testing. Embedded software testing, but that has changed nowadays. So more automation with the help of tools and scripts. I would say there are a lot of languages like Python and Perl, Shell. Shell could be from command prompt or the IDE, etc. So they are all evolved. So due to that, what is happening is the unit of software or the program that can be run independently, and these tools can be applied on those run and can get the result. So what will happen is the more emphasis is on dynamic testing, but to gain the confidence we will augment the dynamic testing with static testing. Okay, static approach or testing, etc. So that is how static testing is complementing to dynamic testing, because some of the methods are impossible or very tedious, or it's like very difficult, or there's no point in doing. Sort of a tests are there. Some of the requirements, it could be some of the unit level verification or validation. All this will be done as part of the static testing. So in software development, static analysis and dynamic testing are two different ways of detecting defects. Unfortunately, they are too often thought of as competition for one another, but it's not a competition basically. And developers are sometimes encouraged to favor one to the exclusion of the other because they are biased because they have implemented the code. They don't want to have different approaches and all that. So they used to be always for one of the approach. So this inaccurate and potentially harmful impression may be consequence of confusion over the role and the power of the next generation analysis tools, basically static analysis tools. So that is why to clean up all this misunderstanding within the development team and testing team, this approach of static analysis separately it has evolved and come up. So definitely any embedded system that they are going to have will have static analysis and coverage, which is done without the program executed. So this is an important aspect in embedded software testing. Next one, static testing. So what are the different types are there in static testing which are used for doing the static testing? So there are three things that are done in the static testing, static embedded software testing: static analysis, and the next one is reviews, inspection, and the test process. Then the testing matrix. All these together are used under static testing to make sure that the reports and the completion and the pass-fail criteria are arrived at. So these are the three different types. So we know that we can do a review of the requirements and the design of the code against what is implemented and what is working. So that can be reviewed. It could be informal walkthrough, peer review, inspection, etc. under reviews. So we will study about different types of reviews and review process is very important because every review has its own process. What are types of reviews? What it will bring basically to go through the existing artifacts and understand manually go through documents, basically what is documented and what is been working. That should be consistent and matching. So that is how they use the reviews and inspection and the test process adopted there. So these are specific to in terms of validating and verifying the intended behavior of the system statically. And static analysis we do with the help of tools and checklists and different categories of static analysis are there. We will study in the next slide. And last one is testing metrics. So we need definitely a metrics to manage, control, report, revisit of the artifacts of embedded software testing. So it's very important because without metrics nothing is complete. You are asked how much of the progress you have made on testing. You should be definitely telling in terms of either numbers or percentage or progress in terms of charts, trends, etc. So all this will be part of the metrics. So with the help of metrics, the program is well managed and controlled. Similarly, the metrics are used in terms of analyzing various artifacts as part of the software testing. You could say that it is a overview, but as part of static testing, this is also important so that the completion is taken as a credit in terms of overall embedded software testing. So 3 types of static testing are done: static analysis. Next one is reviews, inspection, and test process. The last one is testing metrics. So static analysis are basically done with the help of support by different tools. So the tools are applied on the code basically, or the implemented part. So basically we do a analysis of the code. So that is what we do in static analysis. Okay, so let us see each one. What are they? What are the details about that? What does it do? Static analysis. Okay. Definition of static analysis: analysis of a program carried out without executing the program. You know that is a standard definition from the standard BS 79251. The various aspects of analysis we do on the program without that is being executed, or as per below: unreachable code. The code of what we do is analyze the code. By analyzing, what we will discover is there are certain pieces of code, certain software units of the code which are not reachable in the entire execution of the program, or which are dead, sort of a thing. Then parameter type mismatches. That means the parameters that is intended to be used in different functions or categories are not being followed. There is a mismatch between what parameters is supposed to be used and the parameters that are implemented. The next one is possible array bound violations. So what is the meaning of array bound violations? We know that we are trying to access an element or element index within the array, but the value that is being given is outside it. That is outside the boundary value of the array. We are trying to access it. The index of the supplied parameters or whatever it could be will be are used actually. So that is a error. That is a issue with that particular function. The next one is the faults found by compilers. That means the compilers basically used for building the program. We know that build the source code. Suppose let's say it's a C code. So what it does, it generates the obj files or the object files. Then what we do, we link it. Next step is link these objects to generate the executable. In a nutshell, I am just briefing this. So while doing this, there could be errors, there could be warnings, there could be info. All these have to be cleared, because somebody may argue, or a developer may argue, I will clear up the errors, I don't care about warnings. The warnings are sometimes very critical, such that some of the above things like parameter incorrectness is there, some of the objects are properly not used and improperly assigned, then there is a index mismatch or wrong use of the index, and that is leading to a warning, and if you ignore the warning, you could lead into a runtime issue. So all this will lead into a runtime issue. What is a runtime issue? Once we build the executable, what we do is we'll execute that on the target, and the error that is getting because of these errors, warning, info, the fault that is going to come from the program are nothing but the runtime issues. So with the help of static analysis, all these pitfalls will be brought out. Okay, and of course it is depending on the type of language also, the kind of warnings the errors are getting used. For example, missing files could be there, and data mismatch, data type mismatch. So typecasting is wrongly used. Possibly divide by 0 is there. Misuse of variables. So these are some of the typical issues that are there. So divide by 0, because compiler won't throw any error, but warnings could be there. Or if you set the errors to such a level that these are reported, then it will throw an error. So but possibility is that the faults are found by the compilers of such a nature. It could be data type mismatches. There could be missing files. Simply it has ignored and somehow it compiled. It is not a correct way. So all this will be part of the compilers. Of course, MISRA errors. If you have enabled the MISRA check while doing the compilation, also it will throw. You can do severity and normal sort of rules. So better to clear up all these type of sort of errors, like severity errors also definitely we have to clear it up, and normal errors also sometimes leading into some issue while running the program. So all these have to be clearly analyzed and reported. So that is what the objective of static analysis with the help of the compiler reported faults. The next one being program complexity. So there are tools basically which can measure the complexity of a program. So what is the complexity of a program? It again it is a measure of the percentage of, or the measurement of the loops, if statements, cases, switches, and all that. How complex the program is written, how complex the program is going to have it. All this will be part of that. So that is measured with the help of tools basically, because manually it is difficult. I will explain the complexity measurement such as McAfee. It's one of the most popular complexity measurement tool or analysis that they do. So higher the complex or higher the complexity, chances of erroneous is more. So lesser the complexity, chances are less. That means we have a high complexity program having lot of conditions, lot of if statements, while loops, cases, and etc. So there is a possibility that the program has become a complex, and number of lines, of course, that also will be into things. We may have a one single function having 200 lines, and I would consider that as a too huge code to maintain or to test it. Better to split into sub functions and try to use it as less as possible in terms of splitting the overall function. So all this matters in terms of the program complexity. It's very important to avoid such things. So with the help of static analysis, we will discover the program complexity and we will report the number. There is a definite reported number for the complexity of the program. We will study about what is program complexity using a McCabe complexity measurement. There is a formula for that. We will study that. So you see, these are some of the static analysis methods that are used: unreachable code, parameter type mismatches, data type mismatches, divided by 0, possible array bound violations will be there, faults that are found by compilers in terms of errors, warnings, info type of report. All these are considered as faults under static analysis. Those have to be analyzed and fixed. Then the last one is the program complexity. That also will be analyzed with the help of static analysis. So continuation of the static analysis. Static analysis can be used as soon as the code can be compiled. That means code has to be compiled and it should be ready. It is in a good compiled state for the static analysis to be done. Otherwise, static analysis tools may not work properly. So they can find bugs early in the development cycle, and bugs found earlier are less expensive to fix. We know that as we progress in the embedded software development, towards the end, it's very difficult to fix and retest and deliver the product, and it will be more expensive to do that than if the bugs are found in the earlier stages of the development cycle. And static analysis, they do not require program inputs, so bugs can be found and eliminated without incurring the expense of developing test cases. So sometimes what will happen is we may not need a test case. Ideally, it is better to have a test case overall, like in terms of identifying different aspects of the analysis. But more or less, how it is done is manually. It is done with the process that is being laid out, but may not be a need of test case development separately, but the program itself. So we don't need to worry about the inputs to the program and all. So we can eliminate the bugs without incurring the expense of developing test cases. So that is what the meaning of this. So static analysis, they can make it easier and less expensive to develop dynamic test cases. The consequence is they can eliminate more bugs for less expense. So in embedded systems in the industry, basically what I have seen is dynamic analysis is or dynamic testing is done first, and then static testing is done. I think this may not be a right approach to attack a embedded systems, especially those systems having a complex nature. Why? Because some of the issues or the problems can be found during the static testing only, where we do the analysis and issues found in the earlier stages, so that before doing the dynamic testing, this all can be found out. Because the expense of static analysis is always less than dynamic one. So that is why it's very important to do the static analysis. Of course, it may not be 100% because it is just compiled. Some of the issues would not have been fixed in the functionality. Still, the functionality is not matured. So the code is bound to change. The static analysis may get impacted. But to have a first cut of what the program is, to understand what is going on, better to do a static analysis as a first hand information that can be used to fix some of the easier bugs before the dynamic testing can be done. So that is what static analysis is going to be useful. So it may not also have been integrated completely with the rest of the program to find the bugs or techniques, but still we can do a static analysis. We can also go through a single file also, a database also, how it is getting the structure of the program or anything in between this. So all this can be considered for static analysis. So the results are better when the entire program is analyzed, but an analysis of small parts can also be useful. Thus, developers can get very quick feedback on their code and the quality of the code. So that is the idea of static analysis. And during static analysis, so the things that we can do is the percentage of the code, how much have been analyzed, what is the change that is going to happen, and the various analysis aspects of the source code where the potential issues are there. All this can be analyzed with the help of tools. The tools can tell basically the percentage of source code where and all it got issues. So before we start developing the test cases, etc., with the help of the tools. So then the graphical representation of the code properties, we can use it. Basically, the representation could have the following 4 types of reports, such as the control flow graph. So we will study this later. Control flow graph is something like how the control of the program is going to be done and executed. The next one is the call tree. That means what are the total number of functionalities, how are the procedures, how they are getting invoked, and who are all invoking. So both are important here. We will probably go through a tree, call tree with an example tool called understand for C++ from Sky Tools. So call tree is very important. Invoker as well as invoked functions or procedures. So by this we will know how the flow of the program, the control flow is going to be executed when the program is run. Then we have a different events and the sequences that are part of the embedded execution. So sequence diagrams will be there, that is useful for static analysis. So all these part of the code properties are different architectural inputs such as class diagrams also used. So probably I will try to put few inputs on the class diagrams, sequence diagrams, which are useful in terms of representing the code and their properties. So these are all will be analyzed statically. Either it could be with the help of a tool or it could be done manually. So that is how static analysis is done with different aspects of the code. Basically it is done on the code. Okay. The next important thing is control coupling and data coupling. It's a very important item they use, especially they use in aerospace industry. So what is the control coupling and data coupling? Definition from CAST paper. CAST is certification authorities software team. So this is a dedicated team basically. Certification authorities software team. That is what is CAST. So that is a group basically. They will define how the static analysis should be done and all that. So as per that paper, this is done by the organization that is called FAA, which is nothing but a US autonomous organization, federal aviation authority. For any airlines to fly or certify, FAA will help, or FAA will have to mandate that this product is good to fly. So, like it is not only for the entire airlines or the entire aircraft, but also for the different components within the aircraft, the complete avionics buses, the software, the hardware, and communication, whatever we are going to use. So there is a standard. So as per the standards, they will verify and certify. Without the certification, the airlines will not deliver the aircrafts. For certifying that, they use certain analysis documents. So they are nothing but cast papers, that is called. Okay, so what is the definition of control coupling and data coupling from this paper? Data coupling. Data coupling is the dependence of a software component on data, not exclusively under the control of that software component. That means the data that is going to be used in the entire software component, but it is not entirely getting controlled with that component, but it is having a dependence on various other components. That is what the definition of data coupling. The other aspect is control coupling, the manner or degree by which one software component influences the execution of another software component. We know that there are functionalities, those functionalities are divided into various sub functionalities or sub procedures or things. So each one will have a dependency. So how they are binded, so what is the binding between them is what is getting defined in control coupling. So these two are very important. These two have to be analyzed in the static analysis aspect with the help of various analysis tools or references or standards such as task from the FAA team. So with the help of that, the data coupling analysis and control coupling analysis are done. So this will bring the dependency of the data that are exclusively used outside and inside the software component. Also the various components influencing the different components will have some sort of a controlling mechanism. That flow and the binding of the various components also will be analyzed. So with this analysis, control coupling and data coupling will be reported. So this will help in terms of analysis, static analysis that is being reported. Okay. The next one is continuation of static analysis, data coupling example. An example of data coupling is a software component that utilizes parameters with a value that is calculated by a different software component, perhaps being executed at a different iteration rate. Very interesting thing. So we have a software functionality so that utilizes the parameters that are coming as an input with a value, but the values are computed or calculated by a different software component. So there is a coupling between that component as well as the utilized component. So and of course it can continue in the next component also, and it can be updated at a different rate. How are we going to validate that? So that is what this data coupling will bring out. The other one is example of control coupling is a real-time software executive that initiates execution of a software component depending upon external parameters or influence. That means in a real-time embedded systems, we know that external parameters could be a signal or time information or any events, etc. All this will influence in terms of the program flow. So how this program flow is getting identified or executed is all is what we are talking about control coupling. So control coupling example is a real-time software executive. Excuse me. So basically it's a scheduler. So that initiates execution of different components depending on the time. It could be depending on the signals or depending on the conditions or some events or some external flags or triggers are done. So that will have the dependency. So all this will be exercised under the control coupling. So that is what about static analysis of control coupling and data coupling. Okay, so I think we'll study little more on control coupling, control flow analysis. It's also called as control flow analysis. It considers the use of program and its flow. Visual inspection of control flow is also very important, so that you know where the flow is going, who is calling, or who is uh, getting called. Examples: call tree unreachable completely or reachable partially. Parametric issues: the parameters are supplied, but with the help of parameters, the call tree is not reached completely, or the call tree is partially reached, and the program is not executing properly. So all this will be brought out in control coupling and control flow analysis. So it's very important to understand the control coupling and data coupling aspects, and you should not get confused with data flow testing, especially in the data flow coupling and any other testing aspects like we did on white box, black box, and all. These are different aspects. It's part of the static analysis. Okay. The next one is the static metrics that are used for software complexity. So we will go through static analysis with the help of tools, also the testing matrix with the help of McAfee complexity, etc. Followed by that, we will study the reviews inspection in the further sessions. So static metrics are used for static analysis with the help of tools. As I said, software complexity is one of the important aspects of software static analysis. McAfee's complex cyclomatic complexity is called. Measure is one, lines of code is one, fan out and fan in, nesting levels. So these are some of the metrics or matrices that are used. We will try to understand at least the McAfee complexity. What is the McAfee complexity? How it has come. So we know that a piece of program or the software has number of diamonds. Diamonds are nothing but the process or the decision boxes. So more decisions are there in the code, the more complexity it is. That we know that. So statement coverage, decision coverage, and McAfee coverage, all three have to be taken care in terms of coverage aspects. You know, we have studied for white box testing, statement coverage, decision coverage, and all that. So McAfee coverage is also very important in terms of whether we have covered completely. All this will be followed, and dependencies taken care while doing the testing. So there are tools that can measure the complexity of the program. It also presents percentage of loops, if statements, etc. High complexity will have more problems in terms of maintenance, execution, and it is a error prone. Chances are high. Error prone software, but extremely complex programs we need sometimes in terms of closed loop control systems with the help of skilled people that is getting developed. And McAfee complexity. So there are number of decisions in a program or the control flow graph. So here you can see the edges that program has and the nodes that the program has, plus 2 will give you the complexity measure. That is how the calculation is done. And we know that lines of code is also required. So basically lines of code is measurement of size of the program basically. So lines of code is nothing but the executable lines of code. It is not the lines that the program has. It is the lines of executable code, also called executable lines of code. So we will not use the lines of code just, but we'll use the lines of executable code such as a statement followed by semicolon. I am talking about C language. Above that we have a comment. See, comment is also a line, but it is not considered as an executable. Similarly, we have in a if loop or for loop semicolon itself as a one executable line, that is also considered as one line under the LOC. Then we have the fan out and fan in. Fan out is the amount of modules, that is total number of module calls. Modules with high fan out are often found in the upper part of the call tree. That means the higher part of the call tree. We will study about the call tree. So fan out will be more. Fan in is the amount of modules that call a specific module. So you have to understand the difference. Fan out is the amount of modules a given module calls. How many calls it will make? Fan in is the other way, where the amount of modules that call a specific module. That means the current module is called by other modules. So this number of fan out and fan in also one of the static analysis metrics that is used in software testing. So next one is the nesting level. We know that nesting, for example, many if statements nested into each other, getting into a deep nesting level. So if we'll have another if, else, again if, like this, so it will go deep. So this could lead into a nesting. So we have to understand what is a deep level. So this also will be coming under as a edge in terms of McCabe complexity. This also will be measured. So code will be very difficult to understand. So it's more difficult when the complexity or the cyclomatic complexity of the program is high. So simple nesting level is if x is greater than 0, do something, else, sorry, do nothing. So this is one nesting level. Suppose we have more ifs within that, then it will become multiple nesting levels. If x is greater than 0, it will be appropriately aligned. If y is greater than 0, so greater than 0, then do something else, do nothing. Now we have come one deep, we have done. Next is done when x is greater than 0, else do nothing. So this has complexity level as 1. This nesting level is more than 1. Here in this case it is 2 because we have edges, more edges. That is why it's more than 1. We'll try to understand that more in the next slide. Okay. So McCabe complexity is also called as a cyclomatic McCabe cyclomatrix complexity, how it is calculated is E minus n plus 2. So E is nothing but edges, n is nothing but nodes. I'll try to depict this way. So we have program going this way, and we have a flow functionality, flow 1, then we have a flow 2, then we lead into flow 3. Here we have 3 nodes. This can be also called as node 1, can be also called as node 2, and as node 3. So the else part, if it is a diamond, then it can become a node 4. So here we have 1, 2, 3, 4 nodes, and edges you can see 1, 2, 3, 4 minus 3 plus 2. It is 1 plus 2, 3. So this is the complexity of this program is 3. So likewise it is getting calculated. So it's very important to understand cyclomatic complexity or the Meca-based cyclomatic complexity. It's in other words, it is also can be considered as edges or the links in the flow graph, and minus n is number of nodes in the flow graph plus number of disconnected parts of the flow graph, or the plus 2 is the default number that is getting added. Okay, let's try to understand a simple example of cyclomatic complexity. This is from the basically from the reference from web. I can just explain you. In the first one, we have 2 nodes and 1 edge. You can see edge is 1, node is 2, and the P is 1. That is the disconnected part. There is no disconnected part, so only one connection we have. So we use something like Meca as 1 minus 2 plus 2 equal to 1. That is edges, 1 edge, 2 nodes, one edge, sorry, 1 node, 1 edge minus 2 nodes plus 2 will become 1. That is, in other way, it is also in terms of parts, it can be edges minus nodes plus 2p, or simply edges minus nodes plus 2, because mostly the disconnection is going to be very less in many of the flow. It will be usually connected, but considering that also, we can use this formula where the above 1 2p is used. P is the connections, so one connection is there. There is a default is 2, so it will become 1. Complexity is 1. In this case, the flow between different nodes, we can see it will go this way, it will reach here, there is some condition, it will come back here, it will go again, go again. So like this the flow is there. So what is the complexity of this program? You can understand this is something like a for loop or if condition, whatever it could be, but the flow is something like this. So what is the complexity here? You can see one is here, the other one is like this. So 2. It means we have how many edges? 1, 2, 3, 4 edges. We have how many nodes? 4 nodes. 1, 2, 3, 4. I will write it for your understanding. 1, 2, 3. There are 4 nodes, and edge number 1, edge number 2. I consider this as edge number 3. 4, Remember, 4 edges are there. So what will be our Maccabee complexity for this? N E minus N plus 2. Here 4 minus 4 because 4 edges, 4 nodes plus 2. It will become 2. So complexity of this program is 2. Similarly, here another program, you can consider this as a multi-threading parallel task sort of a thing where we have 2 parts. So in this case, the complexity is 2. I will leave it to you how you are going to calculate because we know this formula. In the last one, it is straightforward. You know that there are 5 nodes and 4 edges. 4 minus 5 it will become minus 1 plus 2 1. So single one level of complexity is there in this type of program. So that is what is the definition and understanding of the complexity. So as the complexity increases, the program is having more what is it called, complicated, or the flow is more the control is more deeper. So generally if the complexity is greater than 10, meaning that the complexity is too high and the calls for rework. That means generally in embedded industry, automotive or aerospace we take, the complexity has to be around 10 or less than 10 considering the whole program. If it is more than 10 means the complexity is high. So usually what they do is they will ask to rework on that. For reworking there are different methods and all that. That is all developers work. They will either split the functionality or the conditions that are underneath this complexity to make sure that the Maccabee software complexity is within the limit of 10. The complexity specifies the number of independent paths the program has. So you know that here the path is 2. First path is direct. The other path is from the third node it will come back to second, third, fourth. So 2 paths it can execute. So it specifies the number of independent paths the program has. In the case of here first and last path, the path is only 1. So it is as simple as that. So the star what is mentioned here is a P. In case of disconnected nodes, basically nodes, it will become 2P. So that is what the meaning of Maccabee complexity and its analysis. This has to be analyzed and reported basically. The next one is few more examples. I try to put it based on a book, How to Apply Static and Dynamic Analysis in Practice by Otto Winter. It's a good book. We can study. You can see that. And here some examples I have taken from one of the sample. So this report Maccabee complexity has been reported with the help of a tool called LDRA. LDR is another tool. They use it for finding the Maccabee complexity. So here you can see Maccabee is 10. That means it is just complex. The complexity is just in the normal range. You can see number of independent paths. So one is the one here. You can see 2, 3, 4, 5, to be 6, to be 7 here, and 8, 9, 10 like this. The complexity is being arrived. The tool itself will produce it. You don't have to calculate manually. It's basically with the help of the formula which I have spoken in the previous slide. Edge minus nodes plus 2. Similarly, we have more complex. You can see here the flow of the different edges within the nodes, and the complexity here it is very much. The program is display program, so display has obviously different complexity. The complexity is 20 in this case. The more complexity you can see here, it is very complex, where the complexity is 46. Definitely this calls for a rework. Okay, so that is what is about the complexity control flow analysis, Maccabee complexity. So in the next session we will study about the data flow analysis and the matrix part. So that is the end of the session today.